So in the CATS program, also in the new version CITIC, there are implemented different stochastic model. Okay, and this is one of the most common approach to the problem of the definition of the correlation time series. Okay, my approach is little differences. I think that I'm going to skip some slide, and if you have question about this, you can. Okay, I try to do very fast, and if you have question or you are interested, you can contact me and read the paper. But the idea is that when we are in the stationary, if the stationary condition is satisfied, that means that we have at least at the second order stationary condition, mean and standard variance is constant over all the set of data. We can compute empirical autocovariant functions that we have seen that is correlated to the power spectrum, but so we can analyze our time series in terms of time, and if this stationary condition is satisfied, we can really compute empirical autocovariant function. The estimation of the empirical autocovariant function is based on the data. We do not introduce any model. We say, okay, compute the autocovariant function. Okay, I don't put I don't write the equation of the estimator, but you can find in a lot of statistical book. You find it's like a sort of mean between data that that are in cap of a given distance. So for each point, I compute the distance, the mean with all the points that are distance at the same distance. Okay, more or less. But it's a normal problem in statistics. Also in R is implemented, R software package is already implemented the estimate of empirical autocovariant function. The important is to be that the stationary condition is respected. And for my experience, if you process the data with putting attention in a deterministic model, don't put, okay, I put semi-annual or something like this without looking, check really the time series, we obtain time series that are in this, that respect this condition. So for my point of view, the problem can be solved in an easier way, in a more rigorous way. We have just to check if we are not in the stationary condition, and most of the cases we have in the stationary condition. When you don't respect this, you have to check the time series, and often you are not in this condition because you forgot, for instance, a discontinuity. You didn't realize that there was a discontinuity, probably an unknown discontinuity. You don't have information on this, in, for instance, in your log file, something like this. And the other aspect where we change when I say I put attention to the stochastic model, deterministic model, that in my approach we are really going to see what is a periodogram, and we are going to remove all and just the frequencies that give us stationary residuals. In the most of cases, we have just to remove the annual frequency, and we obtain what we want. But we put the right frequency, not 365.25 days, but the draconic year, or estimation very close to this time. Okay, so is an iteration a recursive method up to we don't have in a stationary condition, and we test this using a statistical test like KPSS test. The test to statistic test to test the stationarity of the residual. This is my approach. If this is not respected, we are going to the stationary condition is not satisfied, we are going to check the time series to see if something has been done in a wrong direction, or otherwise we can use the standard method of flicker noise and so on. There is a lot of literature about this problem. So it's an important aspect of the GPS, of the time series analysis, but also for what we are going to see now. Now we started to say what do we want to know by GPS time series. We want to know interseismic velocity, coseismic, postseismic deformation, and possibly a seismic deformation. But often this part of seismic deformation is not so clear. Often it's in the same order of magnitude of the noise or a little bit, so it's not like in Cascadia where you can really see just plotting your time series. So in this case it's really important to fix in a proper way the deterministic and the stochastic model, because you are using not it's a really combined the two quantity. If you think that if you not remove a linear trend in your data, it's like to put a long correlation in your data, of course. So the two models are really combined, are really correlated, and forgetting for one thing to another introduce misunderstanding. So it means that if I use a not appropriate stochastic model, I probably my residual in the estimation could be affected by some effect, or the estimate of the parameter uncertainties is not correct. To be honest, when the GPS community start to think about the correlation time series, when they realize that the uncertainties in the estimate of the velocity, for instance, was very, very, very little, and say, no, it's not possible, we have a higher noise in the data. So they say, probably because we use a not correct stochastic model. From this point, we started to analyze the correlation in the data. At this time, I think that why the precision is so high, because if you remember in the formula, for instance, in the least square, it depends on the number of observations. Okay. Sigma 0, sigma square, the posterior variances is given by the vector of the residual multiply q minus 1 multiply the vector of the residual, and divided by the number of observation minus the number of parameters. So the number of parameters are few, the velocity, the intercept of the slope, the amplitude of the periodic signal, annual, semi-annual, the discontinuity, so are 10, 20 parameters, not so much. But the time series are very huge. Now we have 20 years of time series with daily solution, daily data. So a huge quantity of data. So this decrease, of course. So what I see now that, okay, we can estimate the slope in a precise way. In some time series, you can draw the slope, and you are more or less close to the real solution because you have a huge quantity of data. It became difficult when you try to estimate the other parameters that are more complicated, more correlated to the noise in the data. So starting from this problem, we started to study correlation in the data to increase our noise. It's funny because it's a geophysics want deformation without error, to be sure. Now it's really, sometimes we have a funny discussion with geophysics that just use prepare model, and your error, your uncertainty is it's disturbing thing. No, you have to say this or this, not I say 3 millimeter, more or less 1 millimeter. No, it's too much. So we try to increase our error instead of reduce, because we thought we are forgetting for something. But now I think that this is quite realistic. It's important to have a good, realistic cofactor matrix, but I think that in some time series, very regular, with a huge quantity of data, you can really estimate the velocity with a very high precision. Okay, this is my point of view, but okay, I invited you to think about this. Okay, we have a network of stations usually. Now, up to now, we have processed just one station. Okay, component for component, we have estimate this time series. Now we have to see all the network, and all the network, in the network there are correlation between stations. Because they are observing in the same time, the same satellites, the same sky, the same space, and so on. So we have to take into account for this spatial correlation and filter our data, because sometimes we find common error due to our processing, our modeling that we have introduced. And there are two approaches. The common mode error, that means we are going to estimate just a bias, a constant values for all the network day by day. For each day we estimate this bias. And the other approach is based on principal component analysis. So the common mode error is a stacking method. So we have our observation. This is what we have estimated with our model. So these are the residual. So it's a sort of mean between all the residual of the station for each day. So for each day, for one day, I have 10 stations. So I have 10 values of the residual for that day. Okay, and we compute the average values for that days, and we remove from the observations these values. Of course, if the stations are not correlated, this value, this mean is equal to 0 or very close. But when you find similar values in the residual are really correlated, so you have a signal that you are going to remove by your station, because you see that is due to some effect in your processing step method. So this is an example. This is a Zimmerwald, it's a Switzerland station, and this is the time series. The red dot are the values, the other one are the error bar. This is the common error that we can, the author have estimate with the constant, with the stacking approach. And if you remove this by this data, you can obtain this. So you can see that the variances of this data is shorter, is a less scattered solution. So we improve the repetition in our time series. And the other approach is the principal component analysis. Now we can also use other different component analysis. Principal component analysis is one approach, but now we are also using independent component analysis, complex independent component. There is a lot of this type of techniques. Principal component analysis it tries to find the similarity between set of data. It's very used also in people that do images analysis when they try to study how are compress a picture or something like this, or to find similarity. So if you have different, for instance, face of different person, principal component analysis trying to find the similarity. So probably a rounded face, the eyes, a nose, the common part of this set of data. Okay, so try to highlight the similarity. And okay. So what we obtain by this are to find common signal between stations. So common mode error is common signal between stations, and but we cannot. This is for removing the common mode error. But this instrument, this approach, this method is very useful also for compute blind signal in your time series, because sometimes we can use to remove this common error. So this is a common signal in my station, and it will be related to the first component, principal component. We are going to see some example after. So if this is a time series, this is the station, another station, and so on, and we put all the stations along the row, and this is different time, we can compute a covariance matrix due to this product, and we can diagonalize this this matrix C using eigenvalues and eigenvector. And we found a new base given by principal components that are the most important, the common component of your data. And using this, you can reconstruct your signal, you can filter, you can reconstruct, using this common base, this common signal, we try to reconstruct the signal, and often is a smooth signal. Do you understand? Okay, probably we don't have time to spend in this part, but it's just to say there are different techniques that we have really to improve our knowledge in processing time series. And one approach is, of course, studying all the part related to the correlation over time of the data using autocovariant function, power spectrum, where we have seen autoregressive fractional moving algebra, and so on. But we have also to improve using also this technique based on blind separation signal, is also called this technique. So not principal component analysis, but other component analysis. It means that we have a set of data, we can find the common signal using principal component analysis, but with other approach we can separate the different component, the different signal that we arrive. is what they call the party problem. If you are in a party with a lot of noise, you can receive signal from a lot of part of the room, from guitar, from people that are speaking and so on. And you have a sum of all these noises, this sound, it depends. And you can ask to separate by what you have recorded in your head, all these source of signal. The same thing we try to apply to the GPS. So, for one thing, we have to remove the common error, but we can also use this technique to separate different sources of signals. The coseismic displacement from postseismic displacement and so on. There is a lot now, you can find a lot of examples in literature. So what we have to do now, if you purchase GPS time series, you have to improve your instruments, what you can use to really process in a proper way the time serial and extract the information that you need. Okay, apart from in the principal component of analysis, you can sort the eigenvector in terms of correlated related angle values, and so these values is related to the variances of the signal. So you know that the angle values related, so you mean the component, the principal component related to the highest values of the angle value have a higher variance, have a higher power. So it means that the most common signal in your data. So is the most part of your data. Okay. These are, for instance, a first component in an example in China. They use the station, so you have a plot of the principal component and how each station has contributed to compute this one. So you have higher values or lower values. And this is the PC order in terms of contribute, in terms of variances. This is to remove common mode error. Or you can also use this to compute. This is there was this I think important paper from Harry, because I think it's present two cases, study case very important. In this case, they have a network of stations, and they realize that some stations, this network is affected by the coseismic deformation due to this Hector mine earthquake. There are no stations in the zone very close to the epicenter, are quite far, but you realize that the effect of this Hector mine earthquake can be recorded also in this station. Okay, and you can see that this was one component, principal component, and you see that there is a jump that can be modeled with this blue line. It gives us the discontinuity due to a coseismic displacement. And okay, they compare the values that have obtained using the principal component analysis with what they predicted using some dislocation model to find if the signal could be correlated with the seismic event and so on. Okay, so there is, no, sorry, it's quite late. We have few time for the SR. Okay, what is another important, okay, now I try to go fast in this part because it is a research part. But now a lot of, from the time series we won't find also slow sleep event or transient, it means that things that now you cannot see, you cannot predict. You have not ecoseismic displacement, postseismic, but are signals that you can find in your GPS time series. In literature, we have seen just for the Tohoku earthquake, the people from Japan found a seismic deformation few days before the earthquake. So in literature now you found a different example that explain that you can find what we call slow sleep event. This is a definition that I take from a presentation of Karim. And so it's not clear which signal we are going to see. At the beginning say we are going to see discontinuity, change in the rates, or other type of signal. When it happened and where, with a discontinuity due to an earthquake, we really know when it happened. We know the time because we have recorded this by our instrument. But with a seismic, we have to find this time looking at the GPS time series. And sometimes you have in a, okay, this is, okay, in Cascadia, you can say, okay, in this time something happened. So you have to find a better way to identify the epoch or the dates when this phenomena started. But you can see, and in this work I identified 34 slow sleep events in this interval. But there are cases, like in L'Aquila, I really studied this, is from one of my paper. We try to see if we can see something. L'Aquila earthquake in 2009 was characterized by 3 months of seismic swarm. And okay, this is my approach, but it's already explained. We already talked about this. I remove for the deterministic model, as I explained before. I reduce for common mode error. I compute a stochastic covariance matrix or model using autocovariant function and so on. We filter the data. Sometimes it's better to filter the data in time, as if you filter the data of this station, you can find a discontinuity. We are going when some weeks before the earthquake. This is a station, was not a station in L'Aquila, but is the station in the area above the Aquila fault, in the Campo Tosto fault. So we apply space filtering using PCA analysis, and we found that there was a clusterization between the station outside this zone and the station inside this zone. And this is the first component of the principal component analysis for the east, north and vertical component. And with the far field, it means the station outside the zone and the station inside the zone. And we find this discontinuity in the east component. And using a Bayesian test, is a Bayesian by the theorem of bias. Okay, there is this approach. I find that the most probably time was 12 of February, or at least one with a very high probability values. And this discontinuity was correlated, this is a zoom, with other observations, looking at, for instance, the cumulative number of foreshock. In this data, you have a jump in this number of shock. Looking at these are the repeaters, the repeater signals. Do you know what is a repeater for the seismic wave, where you have a seismic event very close in time during one day? For instance, I am not the most appropriate person to explain you this, but more or less to give you an idea. And these seismic events are more or less in the same place. It's like you try to...
Ringing effect.
Come?
Per ringing effect.
I don't know if you... If like when you want to broke something and you repeat more or less in the same position the phenomenon. I think that probably in the next course you are going to see, or you can ask to Karim. Sorry, we didn't know. I think that is better that Karim explain you better the meaning of this. This is this was a number of events of the repeaters, and we have an increase of this number around the epoch that we have found analyzed GPS data. And there is also a variation in the ratio between the velocity of the PAS waves. And so we say we have a lot of information, and more or less say that in the same epoch something happened. And okay, oh no, okay, and this was explained like a slow slip event due to a very simple model of fault with a decollement, and a very simple model just using few parameterization of a fault, Campotosto fault, that can explain all this type of sources. Okay, this there are also applications. I talk about this because I really know what I've done, so I can say there is also this is important work because give us the geometry of this part. We found really a decollement for the first time in this area, and this geometry was confirmed by other observations in the after. And okay, we also have a critical attack to this paper, really, but I can discuss with you with some this is attack. People ask us, but probably it's due to atmospheric effect, because they try to correlate this with the water, precipitable water, and so on. But they did. I think that they didn't check really the data, because also in the paper there is a strain fitting of the data, and there was not rain that period. There was a lot of snow, but snow means that the temperature of the soil is constant. You don't have a transmission between the atmosphere and the soil. We know because the temperature is around zero, so you don't have change between the atmosphere and the ground. So this one of the we discuss with people that are studying atmosphere science, but there are also some problems in this. Okay, we have very be careful. This is the reason because now we are studying better local effect, but in this case I'm quite sure that it was not a local effect. And when I'm not sure, I don't put the data. Of course, if you are not sure, you have to continue to investigate. But when sometimes you forgot to say, okay, probably this could be the reason, but after we checked, okay, we did a mistake, but all the data that we have say us, okay, we don't have precipitable or temperature effect on our sites. Okay, this is another story. Allora, so before to